This is a video from section 3.4. We're going to look at more chain rule examples. So if we recall, let h of x equal f evaluated at g of x. So if I want to take the derivative, I take the derivative of the outside function evaluated at the inside function, and then I'm going to multiply by the derivative of that inside function. So again, the directions say find the derivative of the function. And what we're going to do is I want to start off with this example. Now, we're going to let y equal a to the x. Now, a is a number. So a is greater than 0. A does not equal 1. Okay? And so I'm going to rewrite this as e to the natural log of a to the x. Because remember that the exponential and the natural log are inverses of each other, right? And so this is equal to e. Now, the x can be pulled out in front of the log, and so this can be written as e to the x times natural log of a. But remember that natural log of a is just a number, right? And so when I want to look at y prime, I'm going to take e to the x times ln a, but I'm going to multiply by the derivative of that inside function, which is x times ln a. And so this is e to the x times ln a. Remember that the derivative of x is 1, and so you're left with just natural log of a. But remember, e to the x times ln a is just a to the x. And so therefore, y prime is a to the x times ln a. And so, for example 2, suppose we want to apply that. Suppose I let y equal, we'll say 5 to the x squared. If I want to take the derivative, I'm going to apply the chain rule. So I'm going to take 5 to the x squared times natural log of 5. But I'm going to multiply by the derivative of this x squared. This is the inside function. So I multiply by the derivative of x squared. The derivative of x squared is 2x. So this is 5 to the x squared times natural log of 5 times 2x. And so if I write this a slightly different way, I'm going to say y prime is 2x times 5 to the x squared times natural log of 5. And that would be the derivative of 5 to the x squared. Let's do another one. Suppose I had y equals 2 to the t cubed. So if I want y prime, it'll be, I'm going to say 2 to the t cubed times natural log of 2. Okay, so essentially I'm following this formula here. But instead of an x, let's go back, I have a t cubed. But if I want to apply the chain rule, I have to take the derivative of that inside function. So I have to take the derivative of t cubed. But the derivative of t cubed is 3t squared. And so if I write this, I'm going to say 3t squared. I'm going to move that out in front. I'm going to multiply by 2 to the t cubed, okay, times natural log of 2. And this is y prime. Let's do another one. Suppose I have example 4. Suppose, well, I'm going to say g of x is 4 to the c over x. So g prime of x is 4 to the c over x times natural log of 4 times the derivative of c over x. Chain rule. And so this is 4 to the c over x times natural log of 4 times, and the derivative, remember that c is constant, and the derivative, let me make a note up here. The derivative of 1 over x is negative 1 over x squared. And so the c is just going to come along for the ride. So the derivative of c over x is negative c over x squared. So I'm just going to move that negative c over x squared out in front. And so g prime of x is negative c over x squared times 4 to the c over x times natural log of 4. And that's how you do that example. Let's look at a slightly more challenging problem here. If h of x is the square root of 4 plus 3f of x, where f of 1 equals 7 and f prime of 1 equals 4. The question says find h prime of 1. Now, so h of x is the square root of 4 plus 3 f of x. Now, we have to apply the chain rule. So if we want the outer function, we can call this, if you want, we can call it capital F of x is equal to the square root of x. The inner function is, we'll say g of x is 4 plus 3 f of x. So if I want h prime of x, I'm going to take 1/2 of some stuff to the negative 1/2. So this is just power rule, okay? And then I'm going to multiply by the derivative of that same stuff. And the stuff that goes inside is that inner function. So you notice the match here? I'm going to put 4 plus 3 f of x here, but I'm going to put 4 plus 3 f of x over here. Okay? So I'm going to say h prime of x is 1/2 of 4 plus 3f of x to the negative a half. So just power rule. But I'm going to multiply by 3f prime of x. But the question says I want h prime of 1. H prime of 1. So I'm going to replace x with 1. So I get 4 plus 3 times f of 1 to the negative a half times 3f prime of 1. But remember that f of 1 is equal to 7, and f prime of 1 is equal to 4. And so h prime of 1 is 1/2 times 4 plus 3 times 7 to the negative a half. And I'm going to multiply by 3 times 4. So I'm going to move that 12 out in front. So I'm going to say this. H prime of 1 is 1/2. And so you notice 4 times 3 is 12, right? So I'm going to write 1/2 of 12 times something to the negative a half. But that something looks like it's 25. So I'm going to put a 25 here. 2 goes into 12 6 times. So this is 6 over 25 to the half. And so therefore, and remember, 25 to the half is square root of 25, which is 5. So h prime of 1 is 6 over 5. And that's how we do this example. This one's pretty interesting. Let's finish off this video with example 6. This is along the lines of pattern recognition. Suppose I give you the following, and I say, find the 1,000th derivative of f of x equal x e to the negative x. Now, certainly I wouldn't expect you to find 1,000 derivatives, but what we're hoping for is that we start to see patterns. So if I start off with the first derivative, I'm going to take the derivative of x, which is 1, and I'm going to multiply by e to the negative x. And then I'm going to add x times the derivative of e to the negative x. So we got to remember that the derivative of e to the negative x is negative e to the negative x. So if I factor out an e to the negative x, I get 1 minus x. So that's interesting. Let's see what the second derivative brings. So the derivative of e to the negative x is negative e to the negative x. But I'm going to multiply by the derivative, So we took the derivative of e to the negative x, right? And got negative e to the negative x. And we're going to multiply by 1 minus x. And then we're going to add e to the negative x times the derivative of 1 minus x, which is negative 1. So this is negative e to the negative x plus x e to the negative x minus e to the negative x. Okay? So if I factor out an e to the negative x, what it looks like I have in parentheses is x minus 2. take the third derivative. So I'm going to apply the product rule again. Negative e to the negative x times x minus 2. And then I'm going to add e to the negative x times 1. So I get negative x e to the negative x plus 2e to the negative x, so I just distribute in, plus e to the negative x. So if I factor out an e to the negative x, I get 3 minus x. Now, when I took the second derivative, I get e to the negative x times x minus 2. I'm wondering if I take the fourth derivative, will I get e to the negative x times x minus 4? So let's check that. Because if that's true, we probably know the 1,000th derivative, because we get an even number. So if I take the fourth derivative, I get negative e to the negative x times 3 minus x plus e to the negative x times negative 1. And so we get negative 3 e to the negative x plus x e to the negative x minus e to the negative x. And so if I factor out that e to the negative x, what I can say is e to the negative x, that the fourth derivative of x is e to the negative x times x minus 4. It will indeed be e to the negative x times x minus 4. And what that tells me is that if I take the fifth derivative, so notice when with the third derivative, I get e to the negative x times 3 minus x. With the first derivative, I got e to the negative x times 1 minus x. So you notice how that derivative matched the 1. The third derivative, with the third derivative, I got a 3. So with the fifth derivative, I should get a 5. Okay? So if I keep going, so I claim if I get the 1,000th derivative of x, I'm going to get e to the negative x times. So now, 1,000 is even. So when we got to the fourth derivative, we got e to the negative x times x minus 4. So when we want the 1,000th derivative, we're going to get e to the negative x times x minus 1,000. So you have to take enough derivatives to where you start seeing a pattern. And you notice it every step of the way, I was factoring out an e to the negative x, because that's what's going to help me establish that pattern. And that'll conclude this video for section 3.4. And we did 6 examples. 4 of them involved the derivative of a to the x, and 2 of them were some more, I would say, conceptual questions. So, okay, thank you.